So we've stated that the electric field is how charge influences the space around it. So the question becomes, if this is an influence on space, how do we find out about it? So let's start with just taking a charge that in this case we'll label big Q. And what we're interested in is figuring out what the electric field is at some point P in the space around big Q. What we can do is we can take some test charge. So let's label our test charge Q naught. And then we can measure the electric force that our source charge, big Q, exerts on our test charge, little q. And so in this case, hey, it just so happens that the electric force exerted by big Q on our test charge points away from the source charge. We can then take our equation, F equals QE, and use it to figure out what the electric field is. So let's fill in all the details in this equation. This is the equation that describes how the electric force and electric field relate to each other. But let's be clear about precisely what we're describing in this equation. The left-hand side of this equation says the electric force exerted on charge Q naught when placed at point P in an electric field. That is going to be equal to your charge Q naught times the electric field at point P. So what we can do is we can take this equation and basically flip it around, so solve for the electric field, because this now says we've used our test charge Q naught to measure a force. And the force depends on two charges. One of them is Q naught, the one we've placed in the field. The other one is the source charge that's creating the field. So there's still two charges sitting in here in this equation. But what we want to know about is the field itself, and the field itself doesn't depend on the test charge. That once we go measure the electric force to figure out what's going on with the field, we want to divide out the impact of the test charge. This equation for the electric field, right? This basically defines what the electric field is mathematically. What is this telling us about how the electric force and electric field relate to each other? The simplest thing we can state is I can use this equation to think about units. So obviously if I know the units of force are newtons, the units of charge are coulombs, this equation for the electric field tells me that the units of the electric field have to have dimensions of force per charge, which in SI units is newtons per coulomb. So those are the units of the electric field. The other thing that this equation is telling me is, again, what I've got here is I've got a vector equation where I've taken a vector and multiplied it by a scalar. So depending on the sign of this scalar, that tells me how the direction of these two vectors are going to relate to each other. So if my test charge Q naught is positive, then the electric force and electric field will point in the same direction. On the other hand, if Q naught is negative, then the electric force and the electric field will point in opposite directions. So what this suggests is that the easiest way to figure out what's going on with the electric field is basically to use a positive test charge. So again, we'll let our big Q sit out there in space, but what we're going to do is we're going to take a positive test charge and move it around from point to point, see what the force is, because we know that the force and the field will point in the same direction if we use a positive test charge. So what we're going to do is we're going to use our positive test charge as a probe that lets us figure out the field. So let's go back to our situation with big Q. And in this case, let's just be explicit that big Q, let's let it be positive. So when I put my test charge out there, and again, this is now, I'm using a positive test charge as a probe. What I see is that there's an electric force exerted on my test charge where it's being repelled from my source charge, big Q. That tells me that they have to have the same sign. And since I know that I'm using a positive test charge, that means that big Q also has to be positive. If the electric force points away, so the electric force exerted on my test charge Q naught as it's sitting at my point P1, if that points away from my source charge big Q, then that means the electric field must also point away. So here the electric field at point P1 points away from my source charge big Q. Let's move to a different point. So what I'll do is I'll stay along the same line, but I'll come in. Well, I know that if I now take my positive test charge and move it into point P2, two things are going to happen. One is it's still going to be repelled because it's still a positive source charge, positive test charge, so the electric force is still going to point away from my source charge big Q. The other thing that's going to happen is that because I've moved it closer, the electric force is going to be larger. Since I didn't change the test charge, that means that the electric field must also be larger. So again, here I have a situation where because the electric force exerted on my test charge points away from my source charge, the electric field must also point away from my source charge. Well, let's pick a different point, one that doesn't lie along the same line. So again, here's point P3. Put my positive test charge there. Again, it's being repelled from my positive source charge. So I see that the electric force points away from my positive source charge, which means since I used a positive test charge that the electric field must also point away from the positive source charge. It's easy enough to see that my test charge is going to be repelled from any point that I choose to put it at because I have a positive source charge, which means that the electric field is always going to point away from big Q. Well, what if I change big Q? So instead of being positive, it's negative. Well, again, if I go back and think about what's going on at P1, I take my positive test charge, I put it at P1, but now what happens is instead of being repelled as it was before when big Q was positive, now it's attracted. My positive test charge is attracted to big Q because big Q is now negative. So my test charge is being pulled towards the source charge, which again, because I'm using a positive test charge, I changed the sign of the source charge, but not the test charge. I'm still using a positive test charge. That means that the electric field must also point towards my negative source charge. And again, it's easy enough to see that that's going to be true no matter what point you pick. So part of what I can do now is kind of summarize these rules. So for starters, I can use my equation for force. Right, so Coulomb's law tells me that I can calculate the force between two charges, one of which I'm going to call little q as my source charge, the other one I'm going to call q naught as my test charge. They're separated by a distance r. Coulomb's law tells me that that force is going to be given by, it'll have a magnitude of the Coulomb's constant Ke times the product of those charges in absolute values, so I always get a positive number here, divided by the distance between them squared. Again, the r hat tells me that it's going to lie along the line connecting those two charges. My equation for the electric field says, we'll take that equation for the force and divide out the impact of my test charge. That's easy enough to do, and what it does is it gives me an equation for calculating the electric field due to some source charge. And again, technically, this is a point charge, the way that we've set this up, because Coulomb's law was an interaction between point charges. We've used a point charge as our test charge. We've now divided that out. So really, this is the electric field due to a charge Q that happens to be a point charge that sits at a point P in space that is a distance r away from Q. So now r is not a distance between charges, it's the distance from my source charge to some point out in space. The equation we have for calculating the electric field looks fairly similar. I've still got my Coulomb's constant out front, I've still got an r squared on bottom. That distance is now the distance from the charge to a point in space, and notice there's only one charge in my numerator now. So it's not a product of charges, it's a single charge because the electric field only depends on the source charge. It's not an interaction between charges. So what can we summarize here? Basically, this equation is telling us a handful of things. One is the magnitude of the electric field due to some point charge is going to be given by Ke times the absolute value of Q over r squared, where again r squared is the distance from your charge to the point out in space. Ke is still the same. It's the Coulomb constant, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. So this is easy enough to calculate. 2, the electric field is directed along the line that connects the charge Q to the point P. So again, that's our r hat piece there that's saying whatever the line is that connects your charge to your point, the electric field has to lie along that line. And what we've just seen from using our positive test charge as a probe is that there's sort of two rules here. One is that the electric field is going to point away from a positive charge. So if our little q, our source charge, is positive, the electric field will point away at point P. If, on the other hand, our source charge is negative, so little q is negative, then the electric field will point towards the source charge at point P. So if we think about the magnitude for a little bit, one thing that this equation is trying to tell us is that the electric field is proportional to only a single charge. It means a couple of things. One, it means that electric fields are caused by charged particles, right? So you bring a charged particle into empty space, it is going to create an electric field. That electric field is the description of the way that the charged particle influences the space around itself. We don't have multiple charges here interacting. Instead, we have a single charge influencing space. You can think of this as, in some sense, the electric field is how a charged particle announces its presence to other charges. So when you bring another particle up into the electric field created by the first particle, it's going to know that that first charged particle is there because it's going to sense the electric field. Second thing this equation is telling us is that the electric field, its magnitude, goes like 1 over r squared. So again, this is another inverse square law rule. It's just like what the Coulomb's law was. So just like the electric force between point charges fell off like 1 over r squared, the electric field at a distance r away from a point charge falls off like 1 over r squared. So if you move twice as far away, the electric field is going to be 1/4 what it was initially. It'll be 4 times weaker. Key things to understand about the electric field. One, it's a vector field. It's a vector field describing what's going on in space. So at any point P, the electric field can be represented by a vector. As with all vectors, the magnitude and direction of the electric field vectors matter. So they're going to tell you whether it's pointing away from your charge or towards your charge. They're going to tell you whether or not your source charge is positive or negative. The second really critical detail to understand is that to figure out the electric field at some point P in space when you have multiple charges is just the vector sum adding up all the contributions to the electric field from each individual charge. This is known as the superposition principle. It's not any different than when we calculated the net force acting on a charge by adding up the individual forces from the other charges in its vicinity. It's just here we're saying we're going to add up the contribution from all the individual charges to the electric field at a point in space. So if you've got 2 charges, you add together 2 vectors. 3 charges, 3 vectors. As many charges as you've got, that's as many vectors as you need to add together. In a situation like this where we have 2 charges, again, we'll let one be positively charged, the other one will be negatively charged. To figure out what the electric field is at point P, we've got 2 electric field vectors that we're going to need to add together. And so what we're going to do is basically say we need to figure out what the contribution is from each charge. Our negative charge is going to create an electric field that points towards it. Our positive charge is going to create an electric field that points away from it. And so what we're left doing to figure out the electric field at point P is saying we need to do the vector addition problem that says add together these 2 vectors to get the net electric field. So that's going to be the key problem that we're going to work. How do you figure out the electric field in the presence of multiple charges? The nice thing is it's a vector summation problem. And at this point, hopefully, we're pretty squared away in terms of how we want to work vector summation problems.